All right, let's dive into the invisible world of electrochemistry. This is where chemistry and electricity collide, and it's the science that powers pretty much everything, from your phone to an electric car. So let's get right into it.
I mean, really think about that for a second. That little AA battery in your remote, or the big battery in your phone, how in the world does it actually work? It can feel like magic, but I promise you it's pure, fascinating chemistry. And we're going to unpack exactly how it all happens.
At its core, electrochemistry is basically a two-way street. On one side, you have these chemical reactions that just naturally, spontaneously give off energy as electricity. But on the other side, you can use electricity to force a reaction to happen that would never happen on its own. We've got the givers and we've got the takers. So let's meet our first character in this story, the giver. This is the hero inside every battery you've ever used, just quietly doing its thing, generating power from a simple chemical reaction. This right here is the galvanic cell. Sometimes you'll hear it called a voltaic cell. Its defining feature? It's totally spontaneous. The chemical reaction inside wants to happen. And when it does, it generously gives away its energy as electricity. You don't need to plug it in. It just works. So let's break down what makes a giver tick. First, its whole job is to turn chemical energy into electrical energy. And like we said, the reaction happens all by itself. It's spontaneous. Inside, you've got two key parts: a negative anode, which is where the electrons come from, and a positive cathode, which is where those electrons are trying to get to. And of course, the perfect example is a battery. All right, so every good story needs an opposite, right? If the galvanic cell is our generous giver, then it's time for you to meet the taker. And this is it, the electrolytic cell. Now, unlike its generous sibling, the chemical reaction in this cell is non-spontaneous. It absolutely will not happen on its own. It has to be forced, and that force comes from an outside power source. It literally has to take energy from something else to get the job done. So here, the whole energy conversion is flipped on its head. We're going from electrical to chemical. The reaction is non-spontaneous, it needs that external push. And get this, the polarities are flipped too. The anode is positive and the cathode is negative. This is the kind of process we use for things like electroplating. Using electricity to coat a cheap metal with a thin layer of something fancy, like gold or silver. So if you remember one thing, let it be this. Galvanic cells are givers, generate power. Electrolytic cells, the takers, consume power. It's that simple. One makes electricity, the other uses electricity to make something new. Okay, let's go a little deeper here. For the giver, the energy comes from right inside the cell. But for the taker, you have to hook it up to an external battery. Another really key difference is something called a salt bridge. It's absolutely essential in a galvanic cell to keep the charges balanced. But for an electrolytic cell, not always necessary. It's these little design details that make them work so differently. So how do we know? How can we tell if a reaction is going to be spontaneous, if it's a giver or a taker? Well, believe it or not, chemistry has a rulebook for that. And it tells us exactly which chemicals want to give up their electrons and which ones are desperate to take them. And here it is. Now, this chart of standard electrode potentials might look a little intimidating. I get it. But really, it's just a ranked list. It's a hierarchy, showing which elements have the strongest pull on electrons. Think of it like a scoreboard for a game of chemical tug-of-war. That's the million-dollar question, right? A big chart full of numbers is pretty useless if you don't know how to read it, but you'll see the logic is actually really, really simple. It all comes down to 3 simple steps. First, you find your 2 materials on this list. Second, you look at the numbers. The one with the higher, more positive number has a stronger pull. It wins the electron tug-of-war. We call that reduction. And third, that means the one with the lower number automatically loses its electrons. We call that oxidation. It's that simple. The higher number takes, the lower number gives. So, for example, let's find copper on our rulebook. Okay, there it is. Q copper, with a potential of positive 0.337 volts. Now, if we pair copper up with something with a lower value, say zinc, which is way down at negative 0.763 volts, who wins? Copper does, hands down. Its higher potential means it's going to snatch those electrons from zinc in a spontaneous energy-giving reaction. So we've got our givers and our takers, our winners and losers in this chemical game. But why does any of this matter outside of a chemistry class? Well, the answer is it's literally everywhere.
On one hand, you have galvanic cells, the givers, which are powering our entire modern world. Every single device you own that runs on a battery uses this exact principle. But then you have the electrolytic cells, the takers, and they are just as important. They're what we use to get pure metals like aluminum from the earth and to create all sorts of essential chemicals. One generates power, the other uses that power to build our world.
So you see, this isn't just some abstract science. This constant, invisible exchange of electrons, this giving and taking, it's the engine that drives so much of our technology and our industry.
And that, of course, brings us to the future. As we push for better batteries for electric cars, for huge grid-scale energy storage solutions, and for tiny medical sensors that can fit inside our bodies, the fundamental principles of the giver and the taker are at the absolute heart of all that innovation. The next big breakthrough is out there, just waiting to be discovered in this amazing dance of electrons.